This is part 11 of the series Circles, and in this part I'm going to begin with the segments of chords theorem. As the name implies, it's talking about taking two chords that intersect inside a circle and breaking them into separate segments. And the theorem states, if two chords intersect inside a circle, then the product of the lengths of the segments of one chord is equal to the product of the lengths of the segments of the other chord. In other words, AE times EC equals ED times EB. Before we go ahead and use this in an example, let's take a look at the proof and see how this thing works. Here is our setup. We're given that segment AC and DB intersect at point E inside the circle E. So AC and DB intersect at E. We need to prove that EA times EC is equal to EB times ED. And we're going to add in, as usual, we're going to add in some auxiliary lines here. And what we're going to want to do is create some inscribed angles to relate these different angles. And we're going to use the concept of similar triangles. It may not seem obvious at this point, but let's go ahead and write in our auxiliary lines and see if it becomes a little more clear. Now what we have is AD and BC drawn in. Did that with the 2-point postulate. We have triangle ADE and triangle BCE. Now these two triangles can be shown to be similar. That is, their angles, corresponding angles, congruent. If you notice, angle A intercepts arc DC, but so does angle B. Angle B intercepts the exact same arc. And so we know by the inscribed angles of a circle theorem, if two inscribed angles intercept the same arc, then those angles are congruent. And we can see here that angle AED and BEC are vertical angles, so those angles are congruent. We could have also used the fact that angle ADB and ACB both intersect the same arc, and therefore those angles are congruent. It really doesn't matter which one you do. The fact of the matter is that if two angles of one triangle are congruent to two angles of a second, then those triangles are similar. That's the idea behind our proof. And once we have that, then we're going to do some algebraic manipulation to come up with this product equation. So let's get started, and we're going to start out by talking about angle A and angle B being congruent, and we might as well go ahead and use angle D and angle C as well, just to simplify the proof a little bit. So I'm going to say angle A is congruent to angle B and angle D is congruent to angle C. So here we have angle A is congruent to B and D is congruent to C because of the inscribed angles of a circle theorem. So D intercepts AB, C intercepts AB, angle A intercepts DC, and angle B intercepts DC. So now I know that this angle is congruent to this and this to this. Therefore these two triangles are similar by angle-angle similarity. And that'll be our next statement. So now we have that these two triangles are similar. We can set up a proportional relationship using this similarity statement to come up with our target statement. This is possible because if you remember back in our similarity unit, we talked about the fact that if two triangles are similar, then the corresponding side lengths are proportional. And so it's that idea that we're going to start with next. I'm going to go ahead and write a proportion, and then we'll walk through it step by step to see where it came from. Here's my proportion, and the reason is definition of similar triangles. Now let's step through this. What I did was I started with knowing that we had to have an EA here. I started with EA here. So EA is 2, and this triangle EA corresponds to EB. So EA is to EB as, then we went back to the other triangle. We have to have an ED and an EB. Well, ED is in this triangle, so ED is the first and last letters. And go over to the next one. The the first and last letters are EC. And so we have our proportion. So I said EA is to EB as ED is to EC. You could have come up with any other set of values. As long as they match the similarity statement, you're okay. But I wanted to make it match exactly so that we had a streamlined path to the final product. Now, that's all we have to do at this point to get this is to multiply both sides by EC. If we multiply both sides by EC, we have EA times EC. And if I multiply both sides by EB here, I will have ED times EB. So that's all we really have to do is multiply both sides by EC and EB, and we're done. And here's our final value. We multiply both sides by EC and both sides by EB, and we did that using the multiplication property of equality. And our proof is complete. Let's go ahead and work an example and see how this is used practically. In this example, we have two chords intersecting inside the circle, and they're broken up into segments which were given, all except x. So we need to solve for x. So based on the segments of chords theorem, we know that 2 times x, the product of the segments of this chord, equals the product of the segments of this chord, equals 3 times 8. So 2x equals 24, x equals 12. Fairly straightforward idea here. Now let's take a look at an example that requires a little bit more work, but it's the exact same process. Here we're given variables for each one of the segment lengths, and what we're looking for is the length of each chord. So we're looking for HR and CD, which is the length of chord HR and the length of chord CD. The relationship still holds exactly as we had it before. The only difference is we're going to have to do a bit of algebra now. So let's start off with this, and we know that x times x plus 6, so the product of the segments of this chord equals the product of the segments of this chord, x plus 2 times x plus 3. Here we multiply through. X times x is x squared. X times 6 is 6x. Here x times x is x squared. X times 3 is 3x. 2 times x is 2x, and 2 times 3 is 6. Now, when we simplify this, we can see that these x squareds are going to cancel out. If I subtract x squared from both sides, these two terms are going to disappear. So I'm left with 6x equals 3x plus 2x is 5x. Then when I subtract 5x from both sides, x equals 6. So now if x equals 6, I can find these different segments. OR is going to be x, which is 6. HO is x plus 6, which is 6 plus 6, which is 12, which makes HR equal to 6 plus 12, which is 18. Then on the other side, we have CO is x plus 2, which is 6 plus 2, and that becomes 8. OD is x plus 3, 6 plus 3, 9. 8 plus 9, that makes CD 17. Hopefully you found that instructive. The key idea to take away is the product of the segments of one chord equals the product of the segments of the other chord. All right, let's move on to another topic. Continuing with our discussion of segments inside circles, we have a few new definitions that we have to cover. The first one is a tangent segment. A tangent segment is a segment that is tangent to a circle at one of its endpoints. So this segment is tangent to the circle at that point. And generally, the tangent segment has to be outside the circle in order to be tangent. So this segment is a tangent segment. A secant segment is a segment that contains a chord, but it has an external segment along with it. And this external segment is the part of a secant segment outside the circle. So here we have tangent segment, secant segment, and external segment. And the relationships here is what we're going to be discussing in the next theorem that we're talking about, and that's going to be the segments of secants theorem. So let's get on to that theorem and see how these new terms are being used. Here we have an example of the segments of secants theorem. The segments of secants theorem applies when you have two secants intersecting at a common point outside the circle. And the theorem states, if two secant segments intersect at a common point outside the circle, then the product of the lengths of one secant segment and its external segment equals the product of the lengths of the other secant segment and its external segment. A lot of words there. Let's look at it a little more visually here. It's stating that the entire secant segment, the length of the entire secant segment, times the length of its external segment, AC times BC, equals the length of the entire other secant segment, EC, and its external segment, DC. So the entire secant segment times its external piece equals the entire secant segment times its external piece. And that's all the theorem states. Now the proof of this theorem is similar to the proof of the last one. We're going to be using triangles inside this circle, but it's going to look a little bit different, but it's still going to result in a proportion and some algebraic manipulation. So let's go ahead and take a look at that proof and see how this thing comes together. In this proof, what we have is AC and EC intersecting at point C. I've gone ahead and drawn in segment AD and EB, creating two triangles, triangle ADC and triangle EBC. We're going to show that those two triangles are similar, and thereby setting up a proportional relationship. Now you can see that angle 3 intercepts arc BD, angle 2 intercepts arc BD. So we know that those two angles are going to be congruent. Because angle 2 and 3 intercept the same arc, they're congruent by inscribed angles of a circle theorem. Next, we know angle 1 is shared by the two of them, so it's congruent to itself by the reflexive property. And that means that these two triangles are similar by angle-angle similarity. Now we can use this similarity statement to come up with the proportion that's going to give us this product relationship here. And if we start out with AC on one side, we should be able to come up with a relationship. So let's draw in that proportion and see where it goes. So I started out with BC here. So BC in this triangle corresponds to CD in that triangle. Coming back to this one, EC in this triangle corresponds to AC in that triangle. So there's our proportion. Now that's all we have to do to get this statement is to cross multiply here. Multiply both sides by AC and multiply both sides by DC. And we should have this piece. So let's go ahead and do that. So if we multiply both sides by AC, we get BC times AC. Multiply both sides by DC, we get EC times DC. And that is our final statement. So that proves that the product of the entire secant segment and its external piece equals the product of the entire secant segment and its external piece. All right, in the next part, we're going to go ahead and look at the secants and tangents, segments of secants and tangents theorem. So I will talk to you in the next part.